Okay, last but not least, we finally made it to Q4. In scenario 1, a square conducting loop with side length S has total resistance R. The loop is held fixed in the xy plane in an external uniform time-varying magnetic field that is initially directed in the positive z direction, so out of the page. As shown, the z component of the magnetic field changes as a function of time t as described by bz equals b naught cosine 2 pi t over t1, where b naught and t1 are positive constants. Indicate whether the induced current in the loop is clockwise, counterclockwise, or 0 during the time interval 0 to t1 over 4 by writing one of the following. Okay, so this is going to be a super fun Faraday's law / Lenz's law question. Woo! Okay, so first we're going to figure out is our flux going to be increasing, decreasing, or what have you in that time interval. So we're going to want to look at the guts of that cosine. So I'm just going to kind of graph that for a second because I'm also the math teacher at my school. All right, so cosine, remember, goes like this. Cool. So cosine has a maximum at 1, and it's multiplied by b naught. So that's going to start at b naught. And if you remember, the guts, the stuff inside, tells me about the period of my function. So normally my guts, if my guts are t, then the period would be 2 pi. So if my guts are 2 pi t over t1, and I'm going to write it over there on purpose, that tells me that my period is 2 pi over that stuff. Which, if you're not the most mathematically triggy inclined person, so that's going to swing up and be t1. So if you're not the most mathematically inclined person and you don't have a solid grasp on how sine and cosine functions work, you could actually also pull this kind of from your equation sheet. So if we look at our handy dandy equation sheet, that's probably going to be on the simple harmonic motion part, which is down here. Okay, so the period is 2 pi over omega, where omega is the thing inside of your sine cosine attached to the t. So that's where I got that from. I know that from my pre-calc / trig class. So I wrote that down. Yeah. So if you didn't know that from your equation sheet, you could use that t equals 2 pi over omega. Omega is the thing. That's omega. So omega is the thing in front of the t. Anyways, math lesson aside, that tells me that the period of this is t1. So in the time interval 0 to t1 over 4, so t1 would be here, one full period. This would be t1 over 2, which means this would be t1 over 4 right there. So that magnetic field is going to be decreasing. Okay, so B is decreasing from 0 to t1 over 4. Okay, so B is decreasing from 0 to t1 over 4. And so if you remember Lenz's law, we can kind of think of it, I like drawing pictures for it personally. So we have a bunch of magnetic field out of the page. You remember through my loop, I have a nice flux out of the page. Some time goes by, my field is decreasing on that interval, so I have less dots out of the page, which means I need to induce a field that's going to give me dots out of the page. That's going to give me a field out of the page to compensate, because magnetic fields don't like to change. So then from my right hand rule, so let me just write that down. So we're going to induce a field out of the page as a result. So we're going to induce a field out of the page, and from our right-hand rule, out of the page is going to be counterclockwise. Current will be counterclockwise. So current's going to be counterclockwise for that one. That was the worst circle I've ever drawn in my life. Okay. Nice. All right, so now we actually want to derive the expression for I as a function of t in terms of SR, B naught, T1, T, and physical constants as appropriate. All right, so that's going to be the Faraday's law side of it. So if you remember, your induced EMF goes like negative d flux dt. So first we want to figure out our flux. So our flux is technically the integral of b dot dA. In this case, my field and my area vector are parallel. So that's just going to be b times dA. And b only changes with time. It does not change with position. So that means this is just straight up going to be b times a. Love that. Cool. So my flux is going to be b times a. So my flux is going to be b naught cosine of 2 pi t over t1. And then A is the area of my loop. They tell me it's a square. So that area is going to be side length squared. Okay, so that's my flux. So I need to take the derivative of my flux. So my d flux dt. So I'm taking the derivative of my flux with respect to time. So b naught and s squared are going to be constants. The derivative of cosine is a negative sign. Keep all the stuff. 2 pi t over t1. And then chain rule, multiply by the derivative of the guts. So that'd be 2 pi over t1. And that's negative d flux dt. So that's going to end up being positive. All right, so that's my induced EMF. Okay. All right, so that's my induced EMF. Now we want current. So now that we have the induced EMF, we're going to use Ohm's law. We're going to use Ohm's law to get the current. So good old V equals IR. So my current is going to be that induced voltage, or my induced EMF, divided by R. So that's going to be B naught. Actually, I'm going to pull all these constants up front. So that's going to be 2 pi B naught. 2 pi B naught S squared over T1 sine of 2 pi T over T1, and then all divided by R. So I'm going to slap that R, boom, down there. So there's my induced current, and we already said what direction it was in. So I honestly don't care about plus and minus signs at the end of the day, because we already found the direction. Okay, so derive an expression for I as a function of time t. So let's just make sure we don't have any things we're not supposed to. So S, check. B naught, check. T1, allowed. R, allowed. T, allowed. Okay, cool. We don't have anybody extra. We're good. All right. That was pretty straightforward. Love that. I love Faraday's law. It's my favorite topic, to be honest. Fun fact, the rock band drum set pedal works by Faraday's law. Yeah. In senior design, a bunch of my friends had to reverse engineer it, and they were so mad when they found out that Physics 2 existed in real life. Anyway, okay, so part C, in scenario 2, a new square conducting loop with side lengths 2s and total resistance 2r is placed in the same external uniform time varying magnetic field as in scenario 1. Indicate whether the maximum induced current I2 in scenario 2 is greater than, less than, or equal to the maximum induced current in scenario 1. Briefly justify by referencing your expression in part B. Okay. All right, so in part B, we said our current is going to go like 2 pi b naught. I'm rewriting it again for a reason. Please bear with me. RT1 sine of 2 pi t over t1. Okay, so remember that sine is going to have a maximum value at, when this is pi over 2. So maximum value of sine is 1. So at max value, all that crap goes to 1. So my I max in my original scenario is going to be 2 pi b naught s squared over r times t1. So now we are doubling the side length and we're doubling the resistance. So if I double the side length, that's going to give me 2s squared. So I'm going to pick up a factor of 4 in the numerator. And if I double the resistance, I'm going to pick up a factor of 2 in the denominator. So that I max is going to be twice as big. So I2 is going to be twice as big as I1 at its maximum value. So I2 is going to be greater than I1. So when you want to justify your answer by referencing the expression you derived in part B, you actually want to use words for that. So what we could say is maximum value. So maximum current is at that 2 pi b naught s squared over RT1. If we double s, the numerator, so referencing our original equation, so functional dependence, that numerator gets a factor of 4. And the denominator, sorry if my handwriting is unintelligible right now, gets a factor of 2. Factor of 2. So since s squared in the numerator, I2 is going to be bigger. Would be enough for that. Okay, so some conversation about how s squared is in the numerator and 2 doubling it squared over just regular doubling it, that numerator is going to win. Okay? Nice. Awesome. The end. Yay, we did it.